Hi, I'm Professor John Olson at the Hildebrand Department of Petroleum and Geosystems Engineering at the University of Texas at Austin. I want to talk to you a little bit about why you would be interested in studying petroleum and geosystems engineering, and in particular, why it would be a good idea to do that here at the Hildebrand Department. So let me start out talking to you a little bit about the department. We're known as UTPGE, and we are a place of learning and innovation. What does that mean? Well, we have the traditional education endeavor that goes on here. We give bachelor's degrees, master's degrees, and doctorate degrees. We also do research, which involves activities by the faculty, as well as graduate students and other researchers that are employed by the department. Those are kind of the traditional things you expect to go on at a university. We're also very involved in outreach. This is something that not only the faculty but the students get involved in, helping K through 12 students understand the appeal of engineering and also looking at education of the general public. Our student organizations and other things get involved in that. And then finally, we do training for high school teachers, oil and gas regulators, and other groups. A little bit about the numbers of UTPGE. We are the #1 ranked graduate program in petroleum engineering and also the #1 ranked undergraduate program in petroleum engineering, according to the latest U.S. News and World Report survey. We have 25 faculty and about 15 staff. Our undergraduate population is about 380, and we have 160 graduate students. Alumni make a big difference in what makes us a successful department. Alumni engagement are things like, for instance, our name, the Hildebrand Department, comes from a gift of the founding CEO and current chairman of Hillcorp Energy, a Houston-based successful energy company. Mr. Jeff Hildebrand made that transformative gift for which we are named the Hildebrand Department. We also have a retired president of EOG Resources, Gary Thomas, gave the cornerstone gift to make the new energy engineering building possible. This is a building that petroleum engineering and some other departments will move into, all related to studies on the topic of energy, as well as teaching on the topic of energy, which will open in fall of 2021. So if we talk a little bit more about what goes on here in campus, teaching and mentorship is one of our main roles in our interaction with students. We do that in the classroom. We do that in opportunities we give students to go out in the field and get field experience. There are opportunities in the laboratory for undergraduates as well as graduate students research. And then we also have one-on-one interaction between faculty and students in office hours and other kinds of activities. So that's a little bit about the department. Let me talk to you a little bit about why a career in energy is important and attractive. If you think about energy, energy has a huge impact on humanity. The world before the modern energy revolution was basically powered by human and animal physical strength. Food, transportation, and preservation was difficult in this environment. There was no refrigeration. Starvation was a common problem across the world. Productive time was limited by essentially when the sun was out. So you couldn't read at night, you didn't have lighting at night. No electricity, obviously, before the modern energy revolution. And also limited communication and knowledge sharing because of that lack of transportation and also lack of modern technology, which is essentially driven by energy. So life was harder and shorter, and technology development was slow. If we just look at a chart here, we have a plot of per capita oil consumption as a proxy for energy consumption versus per capita income. And you can see there's a strong correlation between increased energy consumption and increased standard of living. You can see up here, one of the top per capita income countries in the world is Norway. That's largely because of their successful oil and gas sector in their economy. You can see some countries lie on a lower slope of income per energy consumed. That's essentially related to the efficiency of their economy. some predominantly European countries and North American countries lie on a steeper slope. It'd be interesting to look at this in a little bit more depth by focusing on the United States, China, and India. So the three most populous countries in the world, and the United States and China are the two largest economies in the world. So let's look at the United States first. We have 325 million people. This is an exercise in big numbers, okay? And we consume each year 100 quadrillion BTUs, okay? So what's 100 quadrillion? Well, that's a whole lot of zeros, okay? 100 quadrillion BTUs. So let's try and put that in perspective. So one way I've found to make this 100 quadrillion BTUs per year of United States consumption more tangible is to imagine we take all that energy and represent it as if it was all burned by driving our cars. So we've got the whole economy is manufacturing, industry, transportation, electricity in your house, running your stove, or refrigeration, all that kind of stuff. So all that energy we use, only a fraction of it actually is used for transportation. But let's stick it all into transportation just so we can get a perspective on how big of a number it is. So we're going to stick everybody in their car, and it'll take 150 miles of driving every day by every person in the country in order to be equivalent to that 100 quadrillion BTUs per year. So to make this even more real, let's think about this as if it were city driving to see how much time we would have spent in our car every day. So in city driving, every man, woman, and child has a car, 329 million cars. City driving is an average of 20 miles per hour. It gives me about 25 miles per gallon. So that would be 7 or 8 hours of driving every day would represent the amount of total energy for all purposes that Americans use each day. Let's translate this to China and India, which are the largest countries in population in the world. So if we were to look at how they compare to the United States, the amount of energy that the United States uses per person every day would represent the amount of energy that 3 Chinese citizens use per day. So if you imagine that car driving around 8 hours a day, in America to have 1 person in it. In China, to represent their energy consumption, there would be 3 people in that car for 8 hours a day. In India, which, like I said, hasn't gone very far up the economic development ladder as a country, there would be 12 Indian citizens in that car 8 hours a day to burn up the equivalent total energy for the country that's burned in the United States. Therefore, you can see per capita, in China, they use 1/3 the amount of energy as the United States. In India, they use 1/12 per person. Another way to look at this is to look at a graph of the total energy consumption by country over the past 50 or 60 years. So on this chart, you can see on the y-axis, primary energy consumed in quads per year, so that's quadrillion BTUs per year, and the time runs from 1965 to 2020. And if we look here at the United States with its population of over 300 million people has been consuming on the order of 90-ish quads per year for the last, pretty much since 2000. Europe has a similar consumption history. All of Europe, all the countries together, has a similar consumption to the United States, but with twice as many people. You can see Russia's down here at much lower consumption. It's also much lower population, as well as Japan. Now, the big countries of interest for future energy demand are China and India. So let's take a look at China. China, with its 1.4 billion people, basically used to be a very small consumer of energy, but since 2000 and this economic boom that's occurred in China over the last 20 years, they've surpassed the United States in total energy consumption. In total energy consumption, if they wanted to be the same per capita energy consumption as the United States, they would be way up there. So they'd have to have another 50% to their energy consumption. So there's potential for every Chinese to have the same standard of living of a typical American. There would still be additional energy consumption that that country would have to increase to. If we look at India, almost the same population as China. Their current consumption is only that of Russia. So they have the same consumption of Russia, whereas Russia has 1/10 the population. This is way below the total consumption in the United States. Now, if we took India and took it to the same per capita consumption as a typical American, India as a country would be consuming off the chart as well. Okay, so the reason why I show you this chart is to show you that for the future, we should expect significant increase in energy consumption around the world. So making that supply reliable and affordable is one of the challenges that a petroleum engineer is trained to do. If we just look at the numbers here, you can see country by country, China has been increasing in their consumption about 5% per year. The United States is slightly declining. That's because our economy is not growing as fast as China's, plus we're becoming more efficient in our energy usage. India is growing at about the order of 6% per year, and Africa, where the amount of energy consumed in Africa is significantly less than these other countries, it's growing at 3% per year. So we've got this energy consumption that we're doing. There's a substantial amount of energy consumption right now and growth for the future. Where does that energy come from? If we look at this pie chart, you can see the biggest component of energy for the United States and for the world comes from petroleum. 37% of our energy that we consume comes from petroleum. 28% comes from natural gas, which is also a commodity that is produced from reservoirs, the same kinds of reservoirs that oil comes from. So it's part of the career focus of petroleum engineers. 15% of our energy comes from coal. This is not something that petroleum engineers work in, but it is called a fossil fuel. And that particular segment of our energy supply is declining. And then renewables, you've heard, are increasing. The big growth area here in renewables that's currently only 10% of our energy consumption is in wind and solar. And then finally, the other major component of source of energy for us is nuclear. Oil is mostly used for transportation. Natural gas is basically substituting now for coal for electric generation. So how are we going to address this energy supply challenge? And this is where, like I said, the careers in energy will be interesting and rewarding in the future, and a big part of that is the petroleum engineering sector. So we already have had a revolution in energy supply. If we look here at crude oil production versus time, look at this burnt orange curve here, and we can see that in Texas, there was a significant decline over the last 20 to 30 years, and then the shale revolution occurred. And in the shale revolution, Texas actually tripled to quadrupled its oil production. The reason why this is interesting is it was predominantly a technology-based improvement in how we evaluate our energy resources. And not only Texas, but the United States went from being an importer of energy to be largely a net zero importer, and we actually export some energy in the form of natural gas. So let's talk a little bit about why shale has become such an important part of our energy production mix. This is an example showing the Barnett Shale, which is basically underground beneath the city of Fort Worth. So if we drill down about 5,000 feet, we'll find the Barnett Shale there. This is a sketch of all the geology up in North Texas. And so how did the Barnett Shale become successful? Well, essentially directional drilling technology, hydraulic fracturing, and innovative materials and fluids largely developed by petroleum engineers and their colleagues at work with small, medium to large size oil companies basically made this technology work. So if we think about the drilling technology that's used now is essentially in the city of Fort Worth and in the vicinity near Fort Worth, we drill down about 5,000 feet and we turn the corner and we can drill as much as 5 to 15,000 feet horizontally and get huge exposure of our wellbore with the shale, and then we introduce hydraulic fractures, which give us extra surface area in the subsurface, and essentially create this whole network of producing wellbore structures that can get either natural gas in this particular case or oil produced out of the subsurface. So what kind of things are going to be important for the future technology in the oil and gas business? A big part of this is going to be cost efficiency, to basically be able to do what we do in a less expensive manner, using less time, and but still protecting the environment and the actions that we do. Another thing that's going to be really important is offshore technology. You can see here a bunch of the equipment, ships and platform construction going on that go offshore. And then ultimately robotics and other sorts of high-tech technologies are going to be incorporated in the oil and gas business. Virtual and mixed reality. This is actually a virtual reality drill rig here that I'm sitting at. And then working in the laboratory, developing different chemicals and fluids, as I said before, to make for a more efficient oil and gas business. Another emphasis for future technology in the oil and gas business is this emphasis on sustainability. We've already talked about energy consumption being correlated with standard of living and economic activity. And in the modern world, energy consumption for decades to come is largely going to mean fossil fuel consumption, basically predominantly oil and gas and a little bit of coal. Renewables will not be significant part of our mix for decades yet to come, the energy transition that people talk about. So since we're going to be burning fossil fuels, the implications are that energy consumption, which is related to humans trying to seek a better quality of life, that energy consumption will generate anthropogenic CO2. And CO2 has become of great interest in the last couple of decades because it's been seen as a greenhouse gas that's related to climate change and potentially global warming. So if we look at CO2 emissions then from different parts of the world versus time, you can see here we have millions of tons of carbon dioxide on the y-axis, that's emissions per year. And here we have time from the 1970s to 2020. And this shows various countries in the world that are major emitters, and it also shows the world emissions. So over here on the right-hand y-axis is millions of tons of carbon dioxide emitted per year by the world. So if we look at this red line with the blue dots, that's the world emissions. So you can see the world is emitting approximately 35,000 million tons, which is 35 billion tons of carbon dioxide per year. If we go over to the by country axis over here, you can see the biggest emitter of CO2 in the world is China, and you can see this curve exactly follows their increase in energy consumption that I showed you earlier. If you look at this, the United States is a green curve. The United States used to be the highest emitter in the world. China surpassed us in about 2005, and you can see since 2005 the United States has been declining in CO2 emissions. This is the emissions for all of Europe. You can see they're slightly below the United States, and then we have some other countries here. Of most interest, obviously, is India. So let's look at some historical events. In about 1993, the United Nations had a meeting related to greenhouse gas emissions and its impact on climate change, and that's the reason why we're interested in CO2 is because its impact on the world climate. The Paris meeting, which you often hear about, the Paris Agreement, occurred in about 2015, right here. And in the Paris Agreement, the United States was committed to reducing its level of CO2 down to this pre-2000 level. And if you look at where the United States is headed, you can see we're on track actually to meeting that without any government regulation that's forced that really per se, but the market forces of natural gas produced from shale that's replacing coal has actually allowed us to reduce our CO2 emissions while still having our economy grow. And the reason for that is natural gas for each unit of energy releases about half the CO2 that coal does. So one of the ways that we're meeting CO2 emission targets for reductions is by fuel switching from coal to natural gas in our electricity sector. What other things are the oil and gas industry doing related to a response to global warming and climate change? There's several things. Carbon capture and storage. This is basically capturing CO2 that comes off of power plants or other industrial sites and storing it in geologic formations, kind of the opposite process of us producing oil and gas. Companies are also trying to reduce their emissions in their operations. Some have gone to totally electric or partially renewable electric in their field operations. The companies themselves, companies like ExxonMobil and Chevron, are diversifying into renewables for actual consumer products as well. And also, they're engaging on the economic, environmental, and technical debate of future energy and how we might transition to a lower carbon source for society's energy needs. Ultimately, at the end, all of these things help to mitigate climate change, and in the end, we need to maintain a reliable and affordable energy supply through this coming energy transition. So to summarize, I've covered a bunch of different topics in this short time, but I want you to see that there's a bunch of exciting things going on in petroleum engineering. And the oil and gas business is vibrant, full of opportunities, and it's a core piece of our sustainable energy future. Our current times with our shelter-in-place orders related to coronavirus and such have basically reduced our consumption of energy because people aren't doing what normally happens in our economic world, and a lot of people are out of work, and so energy consumption is down. But when this is over, and hopefully that'll be soon, we expect the economy to recover and that oil and gas demand, as well as other forms of energy demand, will come back. The other thing I want you to remember is, or that I want you to take away from this talk, is that technology matters, and it requires skilled engineers who are excited to solve problems. So going into petroleum engineering is one of the ways to work on the energy future for the United States and the world. And that technology aspect is something that engineers really excel at. And our department, UTPGE, is a dedicated and successful center of learning and innovation that can prepare you to have a exciting and long career in the energy business. Thanks for your time, and I hope you consider applying or coming to the University of Texas at Austin to study engineering.